Assalamu alaikum students. Today we are going to do quick sort. That is again divide and conquer approach. As this algorithm is again based upon the divide and conquer approach, so the main structure of this algorithm, the recursive part of this algorithm is almost the same. The main difference is between the divide part of merge sort and quick sort. So here we see that the difference between the just for the revision sake, you can see that the merge sort algorithm is taking three parameters: array, start index, and end index. And if the start index is less than end index, then we will calculate the mid. So actually, this part is the divide part, where we are dividing the array, dividing our problem into smaller sub problems, just calculating the midpoints, and then we invoke the same function with the different parameters here, and at the end we conquer it using the merge algorithm. While in quick sort, just like here, we are calculating the mid point to divide the array into two parts. We are also using the same kind of technique, but here it is required a complete process, and that is called here, that is partition. We divide the array into two parts, and then we continue with that one, and the rest is almost the same. We repeat the same calls: quick sort with the array A, starting with the start point and ending at mid -1 point. I will discuss later why we are calling it with -1. And again we call it the second part with starting from the A, starting from mid +1, just like in the merge sort we use the mid +1 till the end. And we need not any part for the conquer this and the problems that we have done, so it is automatically being done like that. Let's start with the basic idea of this sorting algorithm. Let's say we have few numbers. These are 1 2 3 4 5 6 7 8 9 10. These are the 10 numbers starting from 1 to 8, randomly placed in these cells, and we need to sort them. The basic idea of this algorithm is that we randomly pick any element from this array, so any element of your choice, and then move it to the sorted location. So what is sorted location? If we sort this one, if we somehow we are able to sort this array, so we will be getting like these numbers here. Okay, so currently the location of 3 is this one, that is 1 2 3 4 5. So it is at index 5, but after sorting it is at index 3. So currently it is at index 5, and after sorting it would be at index 3. So the basic idea is we pick an element from the unsorted array and move it somehow without sorting the rest of the numbers. Move this number, that is this 3, to the location where it should be after the sorting. So rest of the numbers would be unsorted. There is no sorting like that one. Only this number would be at its sorted position. And if we continue this one with the rest of the numbers, one by one we will be we will be picking the number from the unsorted array and moving it to its sorted location. So at the end iteration we will find all the numbers at their right locations. So that makes it worth doing, and we can find logic in that one that it will be working fine. Taking another example like this one, so that you can understand, make you understand how it works. Then after that we will be doing another example, complete example. So just like here, we just pick randomly an element, suppose this 4. So this 4 is called now pivot. So we have to move this 4 in its sorted location. So that would be, so let's say this is 4 comes up here, and after that there would be few numbers, and before that there would be few numbers. So this is at its right location. So this pivot is now its right location, and this is again unsorted, and this is again unsorted. So we recursively apply the same quicksort method here, and then we do the same thing here, and in that way we divide it into two parts, just like we will be doing in the merge sort. But in this scenario you can see the sub arrays are not of equal sizes. They can be one can be very small, the other can be very large, they can be equal, they can be of different lengths. So this is basically the same logic, and here you can see that this part is neither in this 4 is neither in the right sub array nor in the left sub array. That's why we subtracted we did mid minus 1 and mid plus 1. So mid element, that is the pivot here, is neither in the left sub array nor in the right sub array. After this, the next question that raises to mind is how we should pick this pivot. Then the basic idea says that randomly we can pick any element, but this randomness cannot be implemented when we go for the coding. So we should be designing a criteria that should be very simple, and that can be can be done in a big of one operation. So there comes a three main criterion. So pick the first element as a pivot, pick the first element, pick the last element as a pivot, and pick the middlemost element of the array. So these are the operations that can be done in a big of one time, and you can pick any of these ones. So they work very good. In the book, I think it is done with the first element or the last element. So I'm going to do the next example on the next page with the middlemost, that is the third criteria. So I will be picking the middlemost element as the pivot, and then I will be dividing the array into two parts. Okay, let's say we have this example of randomly generated numbers, and we are going to our pivot selection criteria is the middlemost element. So for that one, so this is starting from index 1 2 3 4 5 6 7 8 9 and 10. There are 10 elements. We pick the pivot. So let's say our pivot is, it would be a value. So if this array is a, so we are going to do is like 2 as our starting index is 1 plus 10 whole divided by 2, that is a of 5. We are getting the rounding the number, so it is fifth element. So that is 1 2 3 4 5 fifth is 9. So 9 is going to be our pivot. If we mark it as in a circle, so that this is our pivot. Now the question is, how can we move this pivot to its sorted location? Okay, so coming back to the previous page, if we have picked 4 as a pivot, then what will happen? So this for all this part, this left sub array is unsorted, right sub array is unsorted, but if this 4 is uh, at its sorted location, then it is very much clear that all the numbers on the right of this 4 would be greater than 4, and all the numbers on the left would be smaller than 4, but they all would be unsorted. So in this way, if we get a pivot, so we need to move all the greater elements from the 4 to the right sub array, and the smaller elements to from the right sub array to the left sub array. So you are moving smaller numbers from right sub array into the left sub array, and you are moving greater numbers from left sub array to the right sub array. And this is what we are going to do in this example. To do that one, to find a number that should not be on in the left sub array, we take a pointer, so let's call it I, and to find a number that should not be on in the right sub array, we should get a pointer like j. Now here we can see that the 18 is greater than 19, so that means 18 is not valid at its valid placement, so it should be into the right sub array. So we will stop here, we will not move forward, but we'll stop here, and then we'll start checking with a j. The value of j is jth location is 15, so 15 is greater than 9, so this is in the right sub array, so that is the right one. So we decrement j by 1 and move to its next location, because j is moving from right to left and I is moving from left to right. Now 3 is smaller than 9, so it's on the wrong location. So you found one element that should not be in the left sub array, and you found one element that should not be in the right sub array, so you just swap these two numbers now. So we just checked on in the left sub array, so the number should be smaller, so we checked that 18 is greater than 9, so we stopped there. And on the right sub array we check 15 is greater than 9, then so 15 is in the right location, so in the legal positions. So we check the next element, that is 3 is greater than 9, so it should be in the left sub array, so we stopped here, and then we swapped 18 and 3, so that is a of I and a of j. So 3 is swapped with 18 and 18 is swapped with 3, so I is at its location and j is at this location. So now we continue with the I1. So here you can see that this is a loop, so loop over another loop. So now 3 is, so we will see that the 3 is less than 9, it is right, so we will move next I. So this is 1 is less than 9, so it is right, so then we move next, so that we are just doing I plus plus. So 6 is less than 9, this is again the right one, it is in the right sub array. So 11, so this is I, so this is 11 less than 9, so this condition is false. We stop here, and then we start doing the same thing with the j. Okay, so this is 18 is, then the condition would be the reverse, 18 is greater than 9, so this is true, So this is in the right position, right subarray. So we move j to the next location here. So this is now 10 is greater than 9, so it is in the right location. So we move to the next position, that is here. So j here. So it is 4 is greater than 9. No, it's not true. So we stop here and then we apply the swap operation. Now applying the swap operation, we get this kind of number. So 4 from here it is moved here and 11 is moved here. So our I is here and j is here. We again start with the I. So 4 is less than 9, so it is true. And then we come 9 is less than 9, so it is wrong. So I is here and it stops here. Then we move to the towards the j. It is 11 is greater than 9, it is true. So move j to the next location. So it is 2 is greater than 9, it is false. We stop here and then we will swap the two numbers. Now we can see that we swapped 2 and 9. So we swapped 2 and 9. So 2 is here, 9 is here, and 9 is was the pivot. So pivot changed its position. So now we have to continue the same thing. We have to do it till the both I and j overlap each other. So 2 is greater than 2 is less than 9, not greater than. So it is true. So I is moved to the next location, that is 9. So it is 9 is less than 9, so it is false. Then we come towards the j. So j is already at the pivot, so j is greater than 9, so that is false. Then we swap. So basically there is no effect of this swap because I and j are at the same positions. So this is the end of the first part of this one, where we have now we have two sub arrays. You can see this is one sub array and this is another sub array. So this is left sub array and this is right sub array, and this is the pivot one. So if we try the indices, so it's going to be, if this is the mid, then it is going to start from the start towards the mid minus 1 element, and this is going to start from mid plus 1 element towards the end element. So that's how that was the reason that we use m minus 1 and m plus 1 in the recursive calls of quicksort. Next we need to do these two sub arrays independently, just like 3 1 6 4 2. So the start index is 1 and ending index is 5. So first of all we will calculate the pivot for this one, that will be the middlemost element. So it would be 6. So we will pick the 6 like this one, and then we'll take two pointers, so that is I and then j here. Okay, sorry for that. So we will do this the same process will apply on this part. We pivot is selected the middlemost element. If you are using some other pivot selection criteria, you will be using that one, so first element or last element or whatever you are using. So then we will start from I and continue till we are overlapped with the j1, and then from j side we will be moving towards the pivot. So overall, few elements are traversed by I and few elements are traversed by j. So overall total traversal in each iteration would be n, that is the number of elements. Okay guys, so if we continue with this one, I'm just skipping few steps. So picking the 6 as a pivot, midmost element. So if we do apply the same process that we had done in the previous one, so we will be having scenario like this one. So pivot will move toward the last location at this one. So the array will be divided into three parts: left sub array and the right sub array and the pivot. So there is no element in the right sub array, so all the elements are in the left sub array, but you have to do the same thing repeatedly again and again. So hopefully you can complete this part also and the rest of the things down there. So you should do that one, and considering the sub array as the whole one, don't think that there are many other sub arrays. Do it very carefully and do it slowly, and you will be able to do it. So now you can see very easily that and this division is not always in the equal parts, like we do in the like the merge or do in the mid from the middle. So there are 5 elements here, there are 4 elements here, but in this scenario you can see that all the elements in the left sub array and there is no element in the right sub array. So the rest of the things you can see that this distribution is not always of equal size. I hope guys you can recall the example on the previous page. Uh, we were repeatedly checking that I is smaller than pivot or not. If the a of I, the ith number at the ith location is smaller than the pivot, we just incremented I. So this is what we've been doing in that part. So this one, while a of I is less than pivot, so I is equal to I plus 1. So if the ith number at the ith location is smaller than the pivot, so it means it is in its right location, that it is in the right left sub, rightly in the left sub array. So in the same way, if we go on the other side, so we were checking a of j's value, jth value at the jth location, and comparing it with the pivot. If the value is greater than the pivot, we think that it is rightly in the right sub array, and we just decremented j so that it can check the next legal number in the right sub array. So first of all, we were checking the numbers on in the left sub array. If we find a number that should not be there, then we stop there and start checking in the right sub array, and then we find a number that should not be in the right sub array, and after that we just swap the two numbers, that is a of I and a of j. Now this is the whole procedure that we have been doing, checking the left sub array and then moving towards the right sub array. We find an illegal number on the left sub array and in one illegal number on the right sub array, then we swap it. But we didn't stop there. We repeatedly did this process until I and j overlapped. So we will do this one while I is less than j. We will be doing it until unless I and j overlap or the value of I remains smaller than the j. Okay. Now here we can see that I have added another condition here. So this is the same condition that is in the outer loop. If whenever you have the same loop control variables inside and in the nested loop, in the inner nested loop and the outer nested loop, then you should add this outer condition of the outer loop into the inner loop, so that the values of the loop control variable do not jump within the inner loop. No. So this is our algorithm. So then again, regarding the analysis of this one, we know that I moves from left towards the right and j is moving from right towards the left, and at some position both I and j overlap at the same number and then they stop. If I has traversed 10 elements and there are total 100 elements, then j would be traversing 90 elements, so overall 100. So if I is moving k elements, then j is moving n minus k elements. So overall it's going to traverse, both I and j is going to traverse a total n elements. So that the time complexity of partition algorithm is theta of n. So you have to remember this one, never forget it again. So the main thing is I moving from left to right and j moving from right to left. At some position they will overlap and this algorithm terminates while returning either S or E, and this element, so the both would be, sorry, not S, but it should be either I or J, anyone. So they would be at the pivot location, and this is going to be captured in the variable mid in the quick sort algorithm, and on the basis of that one we divide the array into three parts: left sub array, right sub array, and the pivot element, and then continue with the sub arrays, left sub arrays and the right sub arrays, and we'll keep on doing until you reach to the one element at sub arrays. Let's start our analysis with the best case analysis. For that one we have to find the worst case analysis, and for that we need to find the worst case scenario. So here is the worst case scenario, that is if we have the number that are previously already given as a sorted one, so 10, 15, 17, 18, 20, 30, and you are picking your pivot selection criteria is the first element, that you are going to pick the first element as a pivot. For that one, if we pick let's say 10 and move it to its sorted location, so it will remain like this one, and the rest of the array would be like this one. Then there would be 15, 17, 18 and 30. You again pick the first one as a pivot, and it will become something like this, and you keep on doing, so you can get all the sub arrays of size 1. So in this scenario, so you are basically picking one element at the one you are reducing only the size 1 at the in the right sub array. The same is with if you pick the last element in the same numbers, it will give you the same scenario.